A 120-volt split-phase system consists of two 120-volt circuits with opposite polarities. The voltage between the two circuits is 240 volts. The waveform is a sine wave with two peaks, one positive and one negative, per cycle. On the other hand, 240 volts step down to 120 volts involves a transformer that reduces a 240 volts voltage to 120 volts. The output voltage has a single 120 volt circuit. The waveform is a sine wave with a single peak per cycle. Yes, the waveforms of 120 volt split phase and 240 volt step down to 120 volts are different. Split phase has two peaks per cycle with a voltage difference of 240 volts between them, whereas step down has a single peak per cycle with a voltage of 120 volts. In addition to the waveform difference, there are other distinctions between the two types of power. Firstly, circuit configuration. Split phase requires two circuits, while step down 120 volts only requires one. Secondly, electrical loads. Split phase is commonly used for residential and small commercial applications with single-phase loads such as lighting and appliances. Step-down 120 volts is often used for industrial and larger commercial applications with three-phase loads such as motors and heavy machinery. Thirdly, wiring. Split-phase wiring is more complex than wiring for step-down 120 volts, as it requires two separate circuits. Fourthly, equipment compatibility. Some equipment may not be compatible with both 120 volt split phase and 240 volt step down to 120 volts. It's important to check the equipment specifications before connecting it to a power source. The 120 volt split phase system is a common electrical distribution method, especially in North America for residential and light commercial applications. It effectively provides two voltage levels, 120 volts and 240 volts, from a single-phase three-wire system. The source of this system is typically a distribution transformer with a center tapped secondary winding. This center tap is grounded, serving as the neutral conductor. The two outer conductors, or hot wires, are each 120 volts with respect to the neutral. However, they are 180 degrees out of phase with each other, resulting in a 240 volts potential difference between them. This configuration allows for efficient distribution of power and the operation of both 120 volts and 240 volts appliances and equipment. The 120 volt circuits are used for lighting small appliances and electronic devices, while the 240 volt circuits are used for high power appliances such as electric stoves, clothes dryers, and air conditioners. The advantage of this system is that it balances the load between the two 120 volts legs, reducing the neutral current and minimizing voltage drop. It also provides a relatively simple and cost-effective way to supply different voltage requirements within a building. The step-down 120 volt system, on the other hand, is derived from a higher voltage source such as 240 volts, 480 volts, or even higher, using a step-down transformer. This is commonly used in industrial and commercial settings where higher voltage distribution is more efficient over long distances. The transformer reduces the voltage to 120 volts for use by various equipment and devices. The waveform characteristics of the two systems are subtly different. In a split-phase system, the two 120 volts waveforms are 180 degrees out of phase, as mentioned earlier. This means that when one waveform is at its positive peak, the other is at its negative peak. The resulting 240 volts waveform is the difference between the two 120 volts waveforms, which is also a sine wave. In the step-down system, the 120 volts waveform is a direct transformation of the higher voltage waveform. The transformer preserves the sinusoidal shape of the waveform but reduces its amplitude to 120 volts. While both systems produce a 120 volt sine wave, the source and the relationship to other voltages in the system are different. In terms of circuit configuration, the split-phase system requires a three-wire circuit with two hot wires and a neutral wire. The step-down system typically requires a two-wire circuit with one hot wire and a neutral wire. The wiring for the split-phase system is more complex because it involves balancing the load between the two hot wires to minimize the neutral current. In contrast, the wiring for the step-down system is simpler because it only involves one hot wire. The choice between the two systems depends on the application and the available voltage source. The split-phase system is well suited for residential and light commercial applications where both 120 volts and 240 volts are needed. The step-down system is better suited for industrial and commercial applications where a higher voltage source is available and only 120 volts is needed for specific equipment. As for equipment compatibility, most 120 volts appliances and devices are designed to operate on either system. However, it is always a good practice to check the equipment specifications to ensure compatibility. Some sensitive electronic equipment may be more susceptible to voltage fluctuations or harmonics, which may be more prevalent in one system than the other. In such cases, it may be necessary to use a voltage regulator or a power conditioner to ensure proper operation. It's also worth noting that the grounding and bonding requirements for the two systems are different. The split-phase system requires a grounding electrode system that is connected to the neutral conductor at the service entrance. The step-down system may require a separate grounding electrode system, depending on the size and location of the transformer. It is important to follow the applicable electrical codes and standards to ensure proper grounding and bonding, which are essential for safety and to prevent electrical shock hazards. Understanding the differences between 120 volts split phase and 240 volts step down to 120 volts is crucial for electrical professionals and anyone working with electrical systems. It allows for the selection of the appropriate system for a given application, ensures proper wiring and grounding, and promotes safety. When dealing with electrical systems, always consult with a qualified electrician to ensure that the work is done correctly and safely. Let's delve deeper into the technical aspects of each system, starting with the 120 volt split phase system. As mentioned earlier, this system is derived from a center tap transformer. The secondary winding of the transformer is divided into two equal halves, each providing 120 volts with respect to the center tap. The center tap is grounded, creating the neutral conductor. The two outer conductors are referred to as hot wires because they carry the current. The voltage between the two hot wires is 240 volts, which is used for high-power appliances. The 120 volt circuits are created by connecting a hot wire and the neutral wire to an outlet or light fixture. The current flows from the hot wire through the load and back to the neutral wire. The 240 volt circuits are created by connecting both hot wires to an appliance, such as an electric stove. The current flows from one hot wire through the appliance and back to the other hot wire. The advantage of this system is that it provides two voltage levels from a single transformer. This reduces the cost of installation and simplifies the wiring. However, it also requires careful balancing of the load between the two 120 volts legs to minimize the neutral current. If the load is not balanced, the neutral current can become excessive, leading to voltage drop and potential overheating. The National Electrical Code, or NEC, specifies the requirements for load balancing in split-phase systems. It requires that the neutral conductor be sized to carry the maximum unbalanced load, which is typically calculated as the difference between the currents on the two hot wires. In addition, the NEC requires that the neutral conductor be grounded at the service entrance to provide a low impedance path for fault currents. This helps to protect against electrical shock hazards and to prevent damage to equipment. Now let's turn our attention to the 240 volt step down to 120 volts system. This system is derived from a higher voltage source using a step-down transformer. The transformer reduces the voltage from 240 volts to 120 volts. The 120 volts output is then used to power various equipment and devices. The advantage of this system is that it allows for the use of higher voltage distribution, which is more efficient over long distances. Higher voltage distribution reduces the current, which in turn reduces the voltage drop and the power loss in the conductors. This is particularly important in industrial and commercial settings where the distances between the power source and the loads can be significant. The step-down transformer consists of two windings, a primary winding and a secondary winding. The primary winding is connected to the higher voltage source, and the secondary winding is connected to the 120 volts load. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. For example, if the primary winding has 240 turns and the secondary winding has 120 turns, the voltage transformation ratio is 2:1, and the transformer will step down the voltage from 240 volts to 120 volts. The NEC also specifies the requirements for grounding and bonding in step-down systems. In general, the secondary winding of the transformer must be grounded to provide a lower impedance path for fault currents. The grounding electrode system must be connected to the grounded conductor at the transformer. In addition, the NEC requires that the transformer enclosure be bonded to the grounding electrode system to provide a path for fault currents in case of a ground fault. The choice between the two systems depends on the application and the available voltage source. If both 120 volts and 240 volts are needed, the split-phase system is the preferred choice. If only 120 volts is needed and a higher voltage source is available, the step-down system is a good option. In some cases, it may be necessary to use both systems. For example, a commercial building may have a split-phase system for the lighting and receptacles and a step-down system for the air conditioning equipment. In summary, the 120-volt split-phase system and the 240-volt step-down to 120-volt system are two different methods of providing 120 volts power. The split-phase system is derived from a center tap transformer and provides both 120 volts and 240 volts. The step-down system is derived from a higher voltage source using a step-down transformer and provides only 120 volts. The choice between the two systems depends on the application and the available voltage source. Understanding the differences between the two systems is essential for electrical professionals and anyone working with electrical systems. It allows for the selection of the appropriate system for a given application, ensures proper wiring and grounding, and promotes safety. Let's now consider the practical implications of these differences in various applications. In a typical residential setting, the 120-volt split-phase system is the standard. It provides the necessary voltage levels for lighting, small appliances, and high-power appliances such as stoves and dryers. The wiring is typically done with 14.2 or 12.2 non-metallic sheathed cable, also known as Romex, for the 120-volt circuits, and 10.2 or 8.2 Romex for the 240-volt circuits, depending on the amperage rating of the circuit. The 14.2 Romex consists of two 14 American wire gauge, or AUG, conductors and a ground wire. The 12.2 Romex consists of two 12 AWG conductors and a ground wire. Similarly, the 10.2 and 8.2 Romex consist of two 10 AWG and two 8 AWG conductors, respectively, and a ground wire. The ground wire is typically bare copper or green insulated. The receptacles and switches are rated for 15 amps or 20 amps at 120 volts. The 240 volts appliances are typically connected to dedicated circuits with appropriately rated receptacles and circuit breakers. In a commercial setting, the choice between the two systems depends on the size and type of the building and the equipment used. In a small office building, a split-phase system may be sufficient to provide the necessary power for lighting, computers, and small appliances. However, in a larger commercial building or an industrial facility, a three-phase system is typically used. A three-phase system provides three separate voltage sources that are 120 degrees out of phase with each other. This allows for more efficient distribution of power and the operation of three-phase equipment such as motors and pumps. In a three-phase system, the voltage is typically stepped down to 120 volts or 208 volts for lighting and receptacles. The 208 volts is derived from the phase-to-phase voltage of the three-phase system. The step-down 120-volt system is often used for powering sensitive electronic equipment such as computers and servers. This is because the step-down system provides a cleaner and more stable voltage than the split-phase system. The transformer isolates the equipment from voltage fluctuations and harmonics on the primary side of the transformer. In addition, the step-down system can be designed to provide a specific voltage level that is optimized for the equipment being powered. For example, some electronic equipment may require a voltage of 115 volts or 125 volts rather than the standard 120 volts. In such cases, the transformer can be designed to provide the exact voltage required. In an industrial setting, the step-down 120-volt system is often used for powering control circuits and instrumentation. Control circuits are used to control the operation of machinery and equipment. Instrumentation is used to measure and monitor various parameters such as temperature, pressure, and flow. These circuits typically require a stable and reliable voltage source to ensure proper operation. The step-down 120-volt system provides the necessary voltage stability and reliability. Furthermore, in certain applications where safety is a paramount concern, such as in hospitals or laboratories, isolation transformers are used to provide an extra layer of protection. Isolation transformers have separate primary and secondary windings that are not electrically connected. This prevents any leakage current from the primary side from flowing to the secondary side, which could pose a hazard to patients or personnel. The secondary side of the isolation transformer is typically grounded to provide a reference point for the voltage. In addition to the voltage level, the frequency of the power supply is also an important consideration. In North America, the standard frequency is 60 Hz or HE. However, in some countries, the standard frequency is 50 HZ. Most equipment is designed to operate at either 50 HZ or 60 HZ. However, some equipment may be sensitive to the frequency and may not operate properly if the frequency is not correct. When using equipment that is designed for a different frequency, it may be necessary to use a frequency converter to change the frequency of the power supply. Frequency converters are electronic devices that convert the frequency of the power supply from one value to another. They are commonly used in applications where equipment is being imported or exported between countries with different frequency standards. Finally, it is important to consider the power quality of the power supply. Power quality refers to the characteristics of the voltage and current waveforms. A power supply with good power quality will have a stable voltage, a sinusoidal waveform, and low levels of harmonics. Harmonics are unwanted frequencies that can distort the voltage and current waveforms. Poor power quality can cause equipment to malfunction, overheat, or even fail. There are a number of factors that can affect power quality, including the load on the power system, the type of equipment being used, and the grounding and bonding of the system. To improve power quality, it may be necessary to use power conditioning equipment such as voltage regulators, surge suppressors, and harmonic filters. In conclusion, the choice between the 120-volt split-phase system and the 240-volt step-down to 120-volt system depends on a variety of factors, including the application, the available voltage source, the equipment being used, and the power quality requirements. Understanding the differences between the two systems and the factors that affect their performance is essential for electrical professionals and anyone working with electrical systems. Always consult with a qualified electrician to ensure that the electrical system is designed and installed correctly and safely. The NEC is a comprehensive set of standards that governs the design, installation, and maintenance of electrical systems. It is updated every 3 years to reflect the latest technologies and safety practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding and bonding, and equipment installation. It is essential for electrical professionals to be familiar with the NEC and to follow its requirements to ensure the safety of electrical systems. In addition to the NEC, there are other standards and codes that may apply to electrical systems depending on the location and the type of installation. These may include local building codes, state electrical codes, and industry standards. It is important to check with the local authorities to determine which codes and standards apply to a particular project. When working with electrical systems, safety is always the top priority. Electricity can be dangerous, and even a small shock can be fatal. Always follow safe work practices and use appropriate personal protective equipment, or PPE, when working with electricity. PPE may include safety glasses, gloves, and insulated tools. Never work on electrical systems that are energized. Always de-energize the circuit and verify that it is de-energized before starting work. Use a voltage tester to check that the circuit is de-energized. Lockout and tag-up procedures should be followed to prevent the circuit from being accidentally re-energized while work is being performed. If you are not qualified to work on electrical systems, do not attempt to do so. Hire a qualified electrician to perform the work. A qualified electrician has the training, experience, and knowledge to work safely with electricity. They will also be familiar with the applicable codes and standards.